two steel shafts connected to each other with the help of two gears. Hi everyone, Mechanics of Materials, Chapter 5, Torsion, Torsion in Gears. So in this problem, we do have two solid shafts which are connected to each other by two gears, and the modulus of the shearing modulus of each of them is 11.2 times 10 to 6 psi. And the allowable shearing stress for each of them is 8 kilopound square inches. We want to know what is the maximum torque which can be applied at the end A for each shaft, and then the corresponding angle of twist at the end A. Let's approach the problem. So the two steel shafts are provided, their length are given, and their diameter is provided, and also the radius of the shafts also are provided. By having the free body diagram of the shaft, as soon as we apply a torsional torque at the one end of shaft AB, the same torsional torque apply to the gear. So for example, if we have the free body diagram of gear B, and you can easily see the effect of forces and summation of moment about the center goes zero, it just gives us a force times radius minus T naught, which is equal to TAB is equal to 0. Do the same for gear C. We can have like summation of moment about C or center goes 0. Then again, the same contact force times the radius should be cancelled out by TCD. And as soon as we have that one, F times 2.45 inches minus TCD goes 0. And solving these two equations, it just gives us a relation between two torsional torque of the gear. So TCD is equal to 2.8 T naught. As soon as we have that one, and by using below kinematics for equal peripheral gears motion, so what does it says? It just says the travel distance in between the two gears remains the same at both sides. So it just says RB times VB is equal exactly the same amount of RC times VC. Contact travel distance remains the same, and that's based off kinematic of mutual motion between these two gears. So we can have the relation of VB is equal to RC over RB times VC, and that gives us a relation of VB and VC. In previous part, we get the relation between the two torque, and now we get the relation VB is 2.8 VC, relation between the two angle of twist, and let's move on to solve our problem. So if we come to torque analysis, for example, for shaft AB, radius, if diameter is 0.75, radius is 0.375 inches, and again TAB is equal to T naught, length is given, and tau for a solid shaft is TC over J. As soon as we have our allowable or acceptable shear, which is 8,000 psi or 8 ksi in the problem statement, and replace it in the equation of tau, and looking for the only unknown of T naught, it just gives us a T naught equal to 663 pound inches. Do the same process for shaft CD. Again, diameter is 1 inches, radius is 0.5, and length is 36 inches, and we are looking for TCD. So TCD is 2.8 times T naught. If we replace that in the equation, it just gives us another equation for T naught, which is 561 pound inches. So we got two a T naught and the minimum is the controlling one. So we need to pick 561 because that's the minimum amount for T naught. And now we have the T naught provided. We do know what the T naught is. That's 561 pound inches. And let's move on to calculate the angle of rotation at end A. So first of all, phi AB in rod AB, that's TAB times length of the shafts over GJ. And we already know TAB is equal to T naught, and that's 561. Replace that in the main equation, and it just gives us and calculate the GJ. J is uh, half of pi r to the fourth times J, which is provided in problem statement, and it just gives us phi A relative to B is almost 2.22 degrees. Do the same process for shaft CD, but we do know TCD is 2.8 T naught, and this is T naught. Replace that in the equation for phi CD. So this is phi C versus D. And if we do so, it just gives us a phi CD is equal to 2.95 degrees. Well, now we do have our phi C. Let's go and calculate phi C. We do know the relative phi, and let's go for the phi C, phi B, and phi A. So since end B of shaft is fixed, so we do know that support D is fixed. So phi C in that case is phi C is only phi C versus D. There is zero here. So in that case, we already know what phi C over D is. That's 2.95 degrees. We already calculate that. We just jot it down here. And phi B is 2.8 phi C. We already calculate this numeric value based off our relation. And if we just plug in the numeric value, it just gives us 8.26 for phi B. And for end A of shaft AB, we have like phi A is equal to phi B plus the relative uh, displacement in terms of rotational angle between A over B. So in that case, we do have uh, 8.26, which is phi B, and phi A over B. We already calculate this relative angle, which is 2.22 degrees. And if you add them up, that's 10.48 degrees. Now we have all of them. We can go for phi C, plug it in 2.95 degrees. Phi B is phi B is 8.26 degrees, and phi A is 10.48 degrees, which is the main goal of this problem. We were looking for phi A, which is 10.48 degrees. Thank you. We'll solve more problems.